Hello everyone, this is Dr.Shalini, Associate Professor, Department of Physics, RMD Engineering College. In this video, you are going to look into what a diffraction is. Diffraction, it refers to the interference or the bending of waves around the corners of an obstacle or through an aperture into the region of geometric shadow of the obstacle or aperture. So in general, it's the bending of light around the obstacles. The diffraction pattern of a red laser beam, when it is made to fall on a plate after passing through a small circular aperture in another plate, is viewed in this diagram as a circular red fringes. The best example of diffraction is the spreading of colors in a rainbow. Here we have the two types of diffraction. The first one is the Fresnel's diffraction. Here the curved wavefront gets diffracted, and the second one is the Fraunhofer diffraction, where the plane wave is diffracted. The Fresnel diffraction, the source or the screen or both are at finite distance from the diffracting obstacle. This is the source, this is the obstacle, and this is the screen. So the source or the screen, they are at a finite distance from the diffraction grating. When you look at a Fraunhofer diffraction, the source and the screen are at infinite distance from the diffraction obstacle. We'll now look into the classification of diffraction, that is your Fresnel and Fraunhofer diffraction. We'll look at the difference. Here we have a cylindrical wavefront, whereas in Fraunhofer diffraction, it's a planar wavefront. The source of the screen is at a finite distance for Fresnel's diffraction, and it is at infinite distance for Fraunhofer diffraction. They move in such a way that they directly corresponds with any shift in the object. So any object that can be moved can be determined by Fresnel's diffraction. Whereas in the case of Fraunhofer diffraction, the position is fixed. This can be occurred on a flat surface, and the Fraunhofer diffraction patterns can be viewed on spherical surfaces. The change as we propagate them further downstreams of the source of scattering. The shape and intensity of this diffraction pattern remains constant. Let us now look into Fraunhofer diffraction at a single slit. This is a slit. You have a lens. The rays of light coming out from the plane wavefront, they made to incident on the screen. When you observe, the path difference can be obtained by BC, which is equal to AB into sine theta. So this is sine theta, as we know, it is opposite by hypotenuse. Here is the angle. So the opposite is BC and the hypotenuse is AB. So sine theta is equal to BC by AB, which is BC is equal to AB sine theta. So this distance of AB gives the value E. So we have the path difference BC to be equal to E sin theta. In general, the conversion of phase difference to path difference is given by the formula phase difference is equal to 2 pi by lambda into path difference. So we have this value of phase difference to be 2 pi by lambda into E sin theta, from which the value of R is observed as A sin ND by 2 divided by sin D by 2. When you take this ND by 2 to be equal to alpha, so it is R is equal to A sin alpha by alpha. The intensity I is R square, which is equal to A square sin alpha by alpha the whole square. The explanation of the intensity of I to be equal to I naught sin square alpha by alpha square is given over here. So from the previous diagram, we have this value of AB. A perpendicular CN is drawn from the center. A perpendicular CN is drawn from the center on the line A. It divides the amplitude R into two parts. So we have here R by 2. This is another R by 2. That's from the triangle ACN and BCN. So as you consider the polygon as an arc of the circle, the angle can be determined using the formula arc divided by the radius. So the arc is n into A naught. The arc is n into A naught. The radius is given by R. So here we have the formula of, in case you take this triangle ACN or BCN, we have the value of sine delta 2 given by R by 2 by AC. Likewise, sine delta by 2 is equal to R by 2 by BC, from which we obtain the value of R to be equal to 2R sine delta by 2. On substituting the value of R to be n A naught by delta, we have R to be equal to n A naught by delta by 2 into sine delta by 2. So as you assume the value of delta by 2 to be equal to alpha, we have the value for the amplitude R to be given as n A naught sine alpha by alpha. As we know, the intensity is directly proportional to the square of the amplitude. We have I is equal to I naught sine square alpha by alpha square, from which we are able to determine the central maxima and the principal maxima. The intensity at the point P remains maximum, and from the principal maxima, the intensity should be 0. Now looking into what a diffraction grating is. See, here we have a white source of light. This is a diffraction grating. As the source of light is made to fall onto this diffraction grating, it gives a large number of parallel slits of equal width that are separated from one another by an equal opaque spaces. Here you find the ray of white light falling on a grating. As the ray of white light falls on an opaque grating, it just gets splitted into various colors due to diffraction. So this is a very large reflecting diffraction grating. And here you can observe an incandescent light bulb which is viewed through a transmissive diffraction grating. Thank you.